we are going to talk about Lenz's law. Now, Lenz's law has everything to do with the direction of the current that you induce. Now, for Lenz's law to occur, first of all, number one, you must first be able to induce EMF. And so we have seen earlier on that according to Faraday's law, you do that when you have a rate of change of flux linkage. And secondly, and very importantly, after you have induced an EMF, there must be some kind of conducting material in which the EMF is induced in. Therefore, you can have an induced current. If you induce an EMF in a non-conducting material, there will be no induced current and there is no Lenz's law. So, consider this example over here. You have a magnet that's moving towards a conducting coil like so. All right. Lenz's law states that the current induced will flow in a way to oppose the change in the flux linkage. Now, the change in the flux linkage, of course, can come about in many ways. Through a magnetic field change, area change, whatever. But typically, right, when we say oppose the flux linkage in the context of Lenz's law, we are opposing one of two things. Number one, you're opposing the change in the magnetic flux density, or number two, you're simply opposing a change in motion. And so I will now demonstrate both of these in a very simple example. So when this magnet approaches the coil, notice that the magnetic flux density is going this way. And so as it approaches, the flux density to the right is getting stronger. Therefore, the coil is going to say, I'm going to oppose that increasing rightward magnetic flux density by producing a magnetic flux density that goes to the left. And so if we use our right-hand grip rule, we can find that the current will indeed flow like this, all right, or more specifically into the page over here and then out of the page on the other side. Okay, sorry, this coil is, let me do that again. So this is supposed to be like a 3D coil. Okay, just imagine it going this way. Current, of course, will be going like this and like that. Okay, and so that's basically what Lenz's law is all about. So if my magnet was moving away from the coil instead, so it's going this way now, what will the coil do? Well, the coil will then say, uh-oh, now the field that's going to the right is getting weaker. And so I have to oppose that by creating a field that goes to the right as well to try to prevent it from getting weaker. And so in this case, the current will then flow this way. And so you see, this is how Lenz's law works. Now, it is important to also understand that Lenz's law is inherently connected to the conservation of energy. Now think about it. Why would your induced current oppose motion or oppose a change in the flux linkage? Well, if you're inducing current, there is some electrical energy being produced. Now, this electrical energy cannot come from nowhere. And so this opposing flux linkage is there because you need some kind of external force to overcome it. You need to force the magnet towards the loop, or you need to force the magnet away from the loop in order to have that induced current. And so that external force, or the work done by that external force, will then, of course, be the one that provides the electrical energy, which is your induced current. And therefore, Lenz's law is inherently related to the conservation of energy.